What actually happens to those individual chains is that if you look at this picture here, all those dotted lines are actually hydrogen bonds. So the individual molecules are in a much larger chain of hydrogen bonded molecules, and they're incredibly rigid. You have so many hydrogen bonds that now it takes a huge amount of energy to break all of these. So that accounts for why wood is such a hard, solid material. And also, I mean, for any plant, and tree obviously is the most dramatic, the structure of a tree, the macroscopic structure, can be explained by hydrogen bonding. It's hydrogen bonds that keep all of those molecules together in the forest and in trees. All right, so that's proteins, that's thinking about sugars. We can also talk about the importance of hydrogen bonding in DNA. So if you think about the characteristic DNA double helix, hydrogen bonds, we have, in a double helix, we have two strands of DNA that you can see are intertwined here. And those two strands are actually held together by hydrogen bonding. So specifically, it's hydrogen bonding between what are called complementary bases within the DNA. So for example, if we look at guanine and cytosine here, you can see that there's several places when they're lined up like this where we can have hydrogen bonds. So in terms of thinking about how these two molecules are lined up, how many H bonds would you expect between these two bases? Yeah, so it's lined up that there are 3 that can form here. So we have an OH hydrogen bond, an HN, and then an HO hydrogen bond that can form. So the other set of complementary base pairs are AT base pairs. And if you look at the way these are lined up here, how many hydrogen bonds can form between A and T base pairs? Yep, so it's 2 that we can form here. We have 1 between the HO, 1 between the NH. And you see that we've lost this nitrogen, this NH group here. And first of all, this would be too far apart anyway for a hydrogen bond. But we can't have a hydrogen bond form when we have a carbon H. Remember, it has to either be a nitrogen or an oxygen or a fluorine, because those are the atoms that are going to pull away enough electron density from the hydrogen to give it the partial positive charge that it needs. So in terms of thinking about DNA, this is a really neat case to consider the actual thermodynamics or the bond enthalpies of the hydrogen bonds. Because, of course, DNA does not always stay in its double helix. When we're talking about transcription, we actually need to unzip or separate this helix into its 2 strands so each individual strand can be copied. So it's really important that hydrogen bonds are strong enough to hold the DNA double strand together, but that they're not so strong that when you actually pull the hydrogen bonds apart to open up the double strand, that you don't want to break all of the covalent bonds in DNA as well. All right, so that's all we're going to say in terms of thinking about thermodynamics in biological systems. Hold on a sec. We have plenty of time left. I want to go over a few clicker questions. I didn't want to give you too long a set of notes because we're switching over to Professor Drennan's going to start lecturing on Friday, so I thought maybe I shouldn't have to have her finish up with my notes. So Professor Drennan will continue talking about thermodynamics and thinking about equilibrium, and then she'll transition that into talking about kinetics. So that's actually what's going to start happening after the exam on Wednesday. But let's take a look, since we do have a little bit of time left, at a few clicker questions, just to make sure everyone has caught what we've gone over so far, and a few reviews for the exam. And I will have this clicker question or one of the ones following be a clicker question quiz, so make sure you are still answering these questions here. So the first one covers what we went over today, so I want you to tell me, and try to not look back in your notes for this, for a reaction where you have a positive enthalpy and a negative entropy change, would you expect this reaction to be never, always, or sometimes spontaneous? So let's take 10 seconds on that. That should be pretty fast. Okay, excellent. 90% is very good. So this should never be spontaneous because we both have the entropy and the enthalpy term contributing to a positive delta G. All right, let's shift gears to a couple questions that are review for the exam. So hopefully these will all be very straightforward for you now. So I want you to think about bond lengths here and tell me which molecule contains the shorter nitrogen-oxygen bond. So we're comparing NO-1 and NO2-1.